Okay, fine. So let us start equilibrium of forces in 3D. So we learned what is equilibrium of forces in 3D, and then actually, so we tried learning so the concepts that are related to vectors in case of 3D. So which is the basics for the equilibrium of forces in 3D. Now here actually, so the fundamental conditions of the equilibrium is there are two different aspects. One is the linear equilibrium, and the second one is so rotational equilibrium. So if the body is under both linear equilibrium and rotational equilibrium, then we say that the body is under equilibrium condition. Why? Because for any body, there is only two different types of motion possible. One is either linear or it may be rotatory. So third one is the general motion. So general motion meaning both linear and circular. Both linear and rotator. So both linear and rotatory, right? So these are the three different kinds of motion actually we will be analyzing. These concepts actually, so we are going to discuss again in so dynamics also, where we are dealing with this general motion there, right? So if the body is under equilibrium condition, so the necessary and sufficient conditions needs to be established based on these two aspects. So one is for the equilibrium of the body, then so R is equal to xi plus yj plus zk. So xi plus yj plus zk is nothing but the components along x-axis, the component along y-axis, and the component along the z-axis. Now this R being a vector, so it will definitely have a direction. Have a direction, which is the line of action of the force, which is the resultant line of action of the force, right? So this resultant line of action of the force, right? So if the body is under equilibrium condition, hence actually this has to result into a null vector. So wherein the x component, if under equilibrium, then R has to be equal to 0. So no resultant force. So hence actually this line of action is nothing but a null vector. Now here, if R is equal to 0, that is possible only x square plus y square plus z square. So this is nothing but the square of the magnitude of this vector. And if this is equal to 0, then the only possible condition is x equal to 0, y equal to 0, and z equal to 0. Got it? So this is the linear equilibrium case, wherein individually all the resolved component along x-axis, all the resolved component along y-axis, and all the resolved component along z-axis individually has to be equal to 0. Then we say that the body is under linear equilibrium condition. Got it? First you note down this, then we are going to discuss this rotational equilibrium. Done? Okay. Then for the rotational equilibrium, so as we discussed in the previous class, right? So all the forces can be resolved into two different parts. One is one force which is equivalent to sum of all the forces, and one moment which is equal to sum of all the individual moments, right? So that term was discussed in the previous class. That means if there is a body, so if there are multiple forces that are acting on this particular body, then all the forces together can be resolved into a single force which is acting at a single point which is arbitrarily chosen. So this is x-axis, and this is y-axis, and this is z-axis. Now if these three are the axes, now all the forces can be resolved into, so one force which is acting at this particular point. So one like this, and one force is like this, and another force is like this. Now this force, right? So this is the point of application of the force for all the forces together. This I have explained. For this particular force, draw a force like this, and exactly opposite to that draw one more force which is exactly equivalent to this. Then actually this one and this one together will form a couple. And this force will be the leftover force. Now similarly for all the forces, individually if you draw at this particular point, so you will be left with one force for each one acting at this location and one couple for each one. So the sum of all the forces is nothing but R is equal to xi plus yj plus zk, which is equal to f1 plus f2 plus f3 plus dash 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 fn, where all these are vectors, right? So this is the resultant force, and similarly the resultant moment is nothing but m is equal to, for each force, right? So there is an associated couple, right? So this one force and this one force. Now actually this is the point of application of the force. Now, so if you take between these two, let us say, so I call this as the point of application of the force as the R vector or R1, then R1 cross F1. So this is F1. So M1 is nothing but so R1 cross F1 plus R2 cross F2 plus dash 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 Rn cross Fn. So this is the sum of all the moments together. Now this can be resolved into L plus Li plus Mj plus Nk. So I call this as G, so that no confusion. So G is equal to Li plus Mj plus Nk. So this is the resultant moment. Now this resultant moment we got from this one, right? That means if I calculate this individually, R1 can be expressed as x1i plus y1j plus z1k. So this is nothing but the position vector, this R1 can be expressed as x1i plus y1j plus z1k, and F1 can be expressed as fx1 into I plus fy1 into j plus fz1 into k. So that is F vector. Now if you do the cross product of this, f1x plus f1y into j plus f1z into k. So you have to calculate the cross product. Similarly for all the vectors. So in a short form, you can express the G as xr into I plus yr into j plus zr into k cross fr into I plus frx plus fry into j plus frz into k. So this is G vector. Now for this one, you just apply R is equal to 1 to n. Got it? So this is the sum of all the individual moments. So this sigma implies that. So individual position vector and individual force vector, take a cross product and then apply sigma on it. You will be getting the resultant moment. Now actually we will take this equation and then try to simplify and then try to arrive at the L equivalent, M equivalent and N equivalent based on this. Got it? You can note down this, we will extend this discussion. So this resultant moment G is equal to Li plus Mj plus Nk is equal to mod I J K and XR, YR, ZR, FXR, FYR, FZR, right? So rather than this, right, F, right, I call this as capital XR, capital YR, capital ZR is nothing but capital XR is nothing but FXR and YR is equal to FYR and ZR is equal to FZR. So with this convention, if you find out the cross product of these two is nothing but I times of, so YR into ZR minus ZR into YR minus J times of XR into ZR minus ZR into XR plus K times of XR into YR minus YR into XR. Now, if you simplify this, this is, so YR into ZR minus ZR into YR into I, XR into ZR, ZR into XR minus XR into ZR into J, XR into YR minus YR into XR into K. Got it? So this is the resultant moment. So here actually I have taken this minus sign to the inside. So like this actually I have written. Now here actually L is equivalent to YR into ZR minus ZR into YR. And then M is equal to ZR into YR minus XR into ZR. And then N is equal to XR into YR minus YR into XR. Now actually this is a randomly chosen force of R. Now if it is applied for all, then actually, so this can be equated to a sigma. So sigma R is equal to 1 to N. Now the same sigma you can apply here. Sigma R is equal to 1 to N. Sigma R is equal to 1 to N. Got it? So all the three forces. So individually each moment actually we have calculated. Now this moment is nothing but L. So whose multiplicated vector is I. So I meaning, so this is the rotational component of the force or the torque component of this particular, all the moments. About I we mean the rotational phenomena with respect to the OX axis, and similarly for Y axis, similarly for Z axis. So this is nothing but a normal vector. So this is individual normal vector. So this component tries to rotate the body about the Z axis, and this component tries to rotate the body about the Y axis, and this component will try to rotate the body about the Z axis. Now all the three together will come into a single force equation or the single moment equation. That moment equation is Li plus Mj plus Nk, which will have a single direction, which is the resultant of all the components together. Got it? So that is nothing but the rotational component direction. So this is a normal vector to all the resultant forces here. So which last line, Vishal? Vishal, I will answer you first and then I will go to Nawaz. Anyway, so see this, I am repeating it. So this is nothing but the cross product. So as and when we wanted to do a cross product, right, we will do in this manner, right, determinant format. So this is the position vector and this is the force vector, rth force and rth position vector. Now sigma r is equal to 1 to n will give all the force components multiplied with the position vector components. Then it is going to give the moment vector. So sum of all the moments, so taken together, is equivalent to Li plus Mj plus Nk. Now here actually, so this is just a determinant finding. So I times of this multiplied by minus of these two, cross multiplication. So these two multiplied minus these two multiplied, minus j times of these two multiplied minus of this one, and k multiplied by AD minus BC. So like this actually we have calculated. Now actually this one, there is a minus sign here, but actually we wanted to express Li plus Mj plus Nk, so that I can keep it here also plus. For that I have taken this minus inside, that's why I have written here. Interchanged these two. Got it? Vishal? Okay. So now actually, so I am just repeating it, the same thing. See this, once we find out the moments, individual force moments actually we have calculated. So moment we mean the force effect which is rotational, right? So that's what is the moment. That we will be able to find out the torque equation, that is R cross F. Now individually if I find out all the moments and add it up together, then it is resulting into a vector Li plus Mj plus Nk, which will be given by this result, which is equal to here. Now here L is equal to, so this first component is the L part of it. Now this L part actually, if you notice, this is I component. I component we mean, so this I vector is nothing but the axis of the rotation of the vector for the moment given by this part. That means the body, let us say this is x-axis, and this body actually tries to rotate in this particular format because of the force components of all the forces together, which will result into a part which is equivalent to yr into zr minus zr into yr. This part actually will try to rotate the body about x-axis like this. And then this part actually will try to rotate the body about the y-axis like this. And this part actually will try to rotate the body about the z-axis like this. Now all the three components of the moments will result into a single moment, which will be given by a single vector Li plus Mj plus Nk. That means, let us imagine this way. So if three persons are pushing one particular block from three different sides, now actually in whatever may be the direction where the maximum force applied, so it will try to push it into that particular direction. So let us say, I will give a simple example here. Now let us say this is one block and one person actually try to push in this particular direction. One person actually try to push in this direction. One person will try to push in this direction. Now actually these are three different forces, F1, F2, F3. Now depending upon the resultant of all the forces together, it will try to assume one direction. Let us say these two forces are more than this force, then actually this force is more than this one, then actually definitely it will try to move in this direction, which is nothing but the resultant direction. Now if you notice, each one is having their own direction, but the resultant is having a single direction, this one, which is the resultant of all, right? Now in this particular direction, everyone is having their own role, but finally it results into a single direction, this direction. Now here also, this part of the component will try to rotate the body about x-axis, and this part actually will try to rotate the body about y-axis, and this part will try to rotate the body about z-axis. Now though each one is having their own rotational axis, the resultant of all the things together, which is nothing but this vector, will have a single direction, which is nothing but the axis of rotation of all the forces together. Got it? So that axis of rotation is nothing but it will try to rotate the body in one particular direction, which will be given by this one. Got it? So though each one is having their own axis, but the resultant of all will be a single direction given by this. Got it? Understood? Okay. So this is actually the moment calculation. Now if the moment is 0, then actually we can say that the body is under rotational equilibrium, which essentially means that individually this component, so if mod g has to be equal to 0, then L square equal to 0, L square plus m square plus n square equal to 0, which essentially means that L equal to 0, m equal to 0, n equal to 0. Now all the three will decide the rotational equilibrium of the body. That means we have got 6 different conditions for the body under equilibrium condition in case of 3D. One is capital X equal to 0, capital Y equal to 0, and capital Z equal to 0. And similarly, L equal to 0, M equal to 0, and N equal to 0. Now, all the 6 conditions will decide whether the body is under equilibrium condition or not. So, this is the difference between the 2D forces versus 3D forces. And 2D also we dealt with only, so that is only planar forces we have taken. Now, this is a random case, which essentially means that the force can be anyway. So it may not be under coplanar condition. So in such cases actually we have to assure this way. Got it? Understood? Now here actually individually we have to assure that the sigma r is equal to 1 to n yr zr minus zr yr equal to 0, and this one has to be equal to 0 and this one has to be equal to 0 depending upon the number of forces. Got it? So for every force actually we have to consider the sum of all the force components. It has to be equal to 0, it has to be equal to 0, and this also has to be equal to 0. Then only we can say that the body is under equilibrium condition. Clear? Any questions on this? Any questions on this? Okay, you can note down this. So if L, M, N are equal to 0, then actually you are saying that so individual forces are equal to 0. Yeah, so like actually if X, Y, Z are 0, then actually L, M, N can exist. But if L, M, N equal to 0, then X, Y, Z, right? So I think it won't exist. Yeah. So your statement is correct, but the counter is not correct. Got it? And then change of the base point. Now here actually, as we have discussed till now, any system of forces can be brought into a point where actually all the forces are acting together, and that is a random point which we have selected based on our own interest. Now that is, suppose if this is the body, and if there are multiple forces that are acting on it, and then you have selected a random point about which you can treat that all the forces are acting at this particular point. This is a randomly chosen point. So let us say this point is O, and then this point is called as the base point. This is the base point. Now, if I shift the base point, let us say I have shifted the base point to here. Now, is there a difference in the force or R actually? Do we have a difference for R or it will be the same? So, this is O dash. So, by referring every force to this particular point, I can calculate the R value. And then by referring every force to this point, I can calculate the R dash value. Now here actually, as we have got the flexibility to select the base point, this is one base point and this is another base point. Now, referring to this point versus referring to this point, is there any difference in the R value, which is nothing but the resultant of all the forces which are acting at this point and acting at this point. So this is R dash and this is R. So can I say that R is equal to R dash, or I should not say that? Can I say that? So one yes, one no. Which one is correct? I think so majority is yes, so that yes is correct. Why? Because see this. So now actually the method what we have adopted to refer to every point to this location is the same force without changing the direction and magnitude I have kept at this location like this. So this is a vertical force, let us say. So this is one force. And then add one counter force at this location. Versus for this particular force, add a force like this and then a counter force like this. Now actually there is no difference between the magnitude and direction. Then we cannot expect a difference in the resultant of all the forces, whether it is acting here or here, right? Understood or not? So do you see any difference? The force acting versus here versus here. The same force is referred, right? The point of application of the force changes, but not the magnitude, but not the direction. Got it or not? So every force is having three different properties. Can somebody tell me what are those three different properties? For any force, there are three fundamental properties associated. What are those three fundamental properties? Can somebody tell me? Magnitude, direction, and there is one more important aspect is there. So one is magnitude and the second one is direction, and the third one and most important is point of application. Point of application of the force. That means suppose if I have a force here, so the same magnitude and same direction, if I apply here versus if I apply here, definitely it will have a different effect on this particular body, right? Here versus here, there will be a different effect. So this will try to move in this direction, this will try to move in this direction. Got it? So that's why, so the point of application of the force does matter. But if you notice, it results into a factor called moment. So movement, actually this is responsible for movement. So the resultant magnitude actually, as long as the magnitude and direction are the same, resultant force magnitude and direction it won't change. But movement can change. Because the point of application here is here versus here. So here and here, these are two different point of applications. Now here actually, for all the forces, one in the upward direction and one in the downward direction for this one, and similarly for this also, if you apply, this is one force and the counter force is applied like this. Now, every force is referred to this location. Now, this one and this one will form the couple. This is in the first case. But in the second case, this one and this one will form the couple. So, couple actually when we are calculating, so the distance actually, this is the R1 dash vector and this is the R1 vector. Now, if you notice, when we calculate the moment, right? So, in the first case, m1 is equal to r1 cross f1. But in second case, the same moment m1 dash is equal to r1 dash cross f1. f1 is not making any change, but r does makes. Hence, actually, the moment will be different, but the resultant force is not different. Got it? Understood or not? Any questions on this? Okay, great. So that means, so even if you change the base point, resultant force actually will not change. But if you change the base point, the moment is going to be changed, right? Now actually we will try to find out the old moment versus new moment. What is the change that is happening? Or if you quantify that, then actually we can calculate easily all the further quantities. That means you have to quantify how much is changing. Now let us do a derivation based on that. So you can note down this. So now actually we do consider the change of the base. This is O and this is O dash, and let us say this is F. Then actually this is R1 dash and this is R1. So these are the position vectors. So this is F1. So when we change the base, then there won't be a change in the resultant magnitude. Magnitude and direction of the force. Since when the base is at O, R is equal to F1 plus F2 plus F3 plus dash 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 Fn. And when the base is at O dash, R dash is equal to F1 plus F2 plus F3. There is no dash, Fn. So therefore R is equal to R dash. You can note down this. Done? Okay. Now, when we calculate the moment, the way we calculate the moment is, when the base is at O, then M is equal to, or the moment is equal to R cross F, right? So this is R cross F. Now, when the base is at O dash, then the moment G dash is equal to R dash cross F. Now here there is a relation between R and R dash. Let us say, so there is a shift of magnitude C from O to O dash. Let us say this is the vector. And then, so this vector is shifted from here to here. This is a C dash vector. And this is R1 vector. This is R1 dash vector. That means C plus R1 dash is equal to R1, right? Can I say that? So this is C vector where you wanted to shift the base from the origin. And this vector is the new vector R dash vector. The sum of these two is equal to R1, correct? So this is based on the triangular law of vector addition. So triangular law of vector addition says that if there are two vectors like this, then the resultant will be this one. So this is R, so if this is P and this is Q, then R is equal to P plus Q is the triangular law of vector addition. So this vector plus this vector will result into this vector. So from triangle, let C be the vector from the initial base point to the new base point. Then, as per triangular law of vector addition, so you can say that R1 is equal to C plus R1 dash. Got it? So if you remove this R is equal to C plus R dash. Now if you keep it here, R is equal to C plus R dash. So if you keep it here, C plus R dash into cross F. This is the new moment. Now if you simplify that, G is equal to C cross F plus R1 dash cross F. Now if you notice, this is the new moment. R1 dash cross, so R1 dash cross F is nothing but the G dash, which is the new moment. So this is G dash vector plus this component, which is nothing but the constant vector C cross F. So you can write that G dash is equal to G minus C cross F. So this is the new moment. Got it? Understood? Got it or not? Any questions on this? G dash is equal to G minus C cross F, where C is the vector drawn from the initial base point to the new base point, which is a constant vector. Understood? Any questions on this? So try to understand this carefully. This is very, very important. Why? Because based on this understanding, down the line classes are going to be there. So now actually we are changing the base point because we have got the flexibility. Now as and when we change the base point, right? So there is a change in the new moment, but there won't be any change in the force. That means the line of action of the force and the magnitude of the force doesn't make any difference, but G is going to be changed. Now G is going to be changed, which essentially means that the magnitude can change, or the direction can change, or the orientation can change. Now in this case, right, so depending upon this new selection, all the values it can change. Now if it is changing, then actually you have got one more understanding here. That means, so if there is a resultant force that is acting in this direction, now by changing this O, or by changing the base point to different locations, maybe on the plane, maybe outside the plane, maybe in the space anywhere if you like it, then you can identify at least one point such that the resultant moment is exactly parallel to the resultant force. Can I say that? Can I say that or not? Right? So by changing the base point, you will be able to identify one particular value of G where the G direction and R direction is one and the same. May be parallel, may not be on the same line. Right? So these two vectors can be parallel depending upon the base point selection. Now that scenario we are going to analyze in the upcoming classes. Right? So but you have to get an understanding of this, what we are doing it here. Got it? So note it down. Okay. So there is a concept called wrench. Right? So this wrench concept is just now whatever I have explained. Wrench is nothing but a combination of the resultant force whose resultant moment is parallel to the resultant force then the resultant force R and the resultant moment is said to constitute a wrench. We say that these two are constituents of a wrench. Got it? And based on the previous understanding, we can state one theorem. Any system of non-coplanar forces can result into a wrench. Right? Any system of forces, there is a theorem. Any system of forces generally results into a wrench. Generally results into a wrench, right? So in the case of wrench, so R can be expressed, so R and G are parallel, which essentially means that R can be expressed as some constant into G. Reverse manner. P can, so both are one and the same, but the relation is different. So G can be expressed as PR. This is the standard convention. So each vector can be expressed as a scalar multiplication of the other vector. Now this value P is called pitch of the wrench. This is the pitch of the wrench. Got it? So any system of forces generally results into a wrench depending upon the selection of your base point, because the base point can be placed at infinite locations. Now at least you will be able to find out one point wherein the resultant moment is parallel to this R value, and that scenario is called as the wrench. So in case of wrench, So G can be expressed as P into R. So only in non-coplanar. Let me think over it. Yeah, that's correct. So that is actually only in non-coplanar only it happens like that. But actually in case of coplanar forces, right? So it won't happen. See this. Suppose if there is a force like this and if there is a force like this, and then whatever may be the point of base actually you select it, the resultant torque is always having a direction which is perpendicular to this board, which is normal to all the forces. So resultant moment direction is always same. So, but this force, right? So, whatever may be the point of the force you selected, there also the resultant magnitude and the resultant direction is always same in case of coplanar forces. So, forces anyway, no change whether it is a coplanar forces or non-coplanar forces. But coming to G, which is the moment, in case of non-coplanar forces, so the direction can change in any direction. But in case of coplanar forces, the direction of the resultant moment is always same, irrespective of the base point. Got it? Because these are coplanar forces. These directions anyway don't change irrespective of the base point. Now, the moment is always perpendicular to the plane. Then that also won't change, right? So, this is applicable only for the non-coplanar. You can specify that. Done? So, this is about equilibrium of forces in 3D, the base concepts, right? So, tomorrow actually we are going to discuss, there is something called the central axis and the calculation of this pitch of the wrench and the relations between all these things, right? So, it will take around 2 classes to complete all these aspects. So, after that actually we will start with a different topic. So, did you find this interesting, this topic? Yeah. So, and that too actually many people feel that actually, so this is one of the tough topic, but ideally it's not. As long as you are good at vectors, there is no complexity in it. This is very, very easy topic, right? So, if you notice whatever the problems we solved, actually whatever the concepts we have discussed, so it is pretty simple as long as you are good at vectors. And for the first topic, you should be good at even the geometry also. So, those are the only 2 requirements that you need to have a complete control on this particular topic. Even in the dynamics also, it will be more or less vectors only we are going to deal with. So, more systematically or mathematically we are going to deal with. So, it's not a tough topic to be specific. Got it? Yeah. So, that's all for today. So, in the next class actually I am going to discuss the calculation of the pitch of the wrench and points at central axis. There is something called central axis. So, that also we are going to discuss in the next class and the relations associated with it. Yeah. Good night.